Okay, so how do we use the concept of utility or utility functions to, how does that change the calculations that we were doing before? Well, so what I'm going to do is I'm going to assume that the utility function is equal to this formula that I have right here. So you'll see that this utility function is quite similar to the utility function that we had in Unit 2 when we were studying firms. Okay, remember that we picked this square root formula, okay, because if I take this function, if I graph the square root formula, it follows this kind of bow-shaped curve that's very similar, okay, to these kinds of curves that exhibit the law of diminishing returns. Okay, so I'm going to go to my calculator here, my expected value calculator here, and finally now we're going to be using these two columns, okay, the utilities. And remember, okay, recall that what we were interested in understanding is why people seem to be so risk averse when it comes to this heads or tails game, right? You offer somebody $50 for sure versus you offer somebody this gamble, okay, of getting heads or tails 50-50. Almost everybody chooses the $50 for sure, even though the expected value of the game is also $50. Okay, so utility will sort of let us understand the situation better. It'll sort of break the tie, so to speak, between these two competing situations. And what we'll find is that even though the expected value of the uncertain game is the same as the sure thing, the expected utility of the game is actually a lot lower. Okay, so it sort of makes sense why people would choose to get the sure thing if they're maximizing expected utility, not expected value. Okay, and so, so hopefully that makes sense. All right, the expected utility, instead of being the amount of money that you expect to win or lose from a situation on average, it's like the amount of satisfaction that you expect to get out of that situation, and that's not always going to be equal to the expected value, the amount of money you expect to get. Okay, so let's do this calculation. Calculation is very straightforward. Okay, all we're going to do is we're going to use the utility function. So, okay, so for example, in this situation, here's my $100 payoff. But what is the utility of $100? Well, we simply need to plug that into the utility function. Okay, and the utility function in this case is the square root of 100. Okay, now obviously that's 10. But I'm going to take my time and actually put the formula in there. I'm going to show you guys how to do it. So calculate the expected utility of $100. I would simply type in equals, and then I would type in the square root. So in Google Sheets or Excel, square root is SQRT. Okay, and then I'm going to click this 100 over here, press enter, there's 10. And then if I drag this down, this will compute the next one. Square root of 0 is 0. Okay, and so you can see here's my utility of here's my utility corresponding to each of these payoffs. I take these utilities and multiply by the probability of each one, and here is those values, and then I take them and I add them up, and here's my expected utility. Okay, so the expected value of this game is $50. The expected utility of this game is 5 units of utility. Okay, 5 units of satisfaction. Okay, so that's the expected utility of the game. Okay, what is the expected utility of getting $50 for sure? Well, that would just be the square root of 50. And if I compute the square root of 50 and compare it to the expected utility of the game, you can see actually the expected utility of $50 for sure is 7 units of satisfaction. Okay, so if what you're maximizing is not expected value, but expected utility, then it makes sense that you would prefer the sure thing, which gives you a utility of $7, as compared to this game, which only has an expected utility of 5. Sorry, I said dollars, but not $5, but 5 units of utility. Some economists call that utils. Okay, so 5 utils of utility. Okay. Okay. So I hope that example makes sense. Okay, and what we'll find is that this concept of utility functions and expected utility is actually quite useful. There are a lot of situations where if you're looking at things strictly from the standpoint of expected value, it doesn't make sense. You can't make sense of the situation. But if instead you look at expected utility, then the paradox or whatever seemed to not make sense is going to be resolved. Okay, so let's look at one final example. Okay. And this is yet again a situation where the expected value doesn't seem to work properly. Okay, and so this involves a game, a kind of more complicated game in the following form. Okay, so suppose we are again flipping coins. Okay, and suppose we flip the coin, and if it lands heads, you get $2, and you also get to play again. And if it lands tails, then the game simply ends. Now, on each subsequent flip, the payoff is doubled. Okay? So for example, if you flip 2 heads in a row, for that second flip, instead of winning $2, you would win 4. And if you get 3 heads in a row, instead of being paid $4, you would be paid 8. So essentially, you're paid double the amount of money for each head that you get. And whenever you finally get a tail, the game will end. Okay? So here's my question for you. How much would you be willing to pay to play this game? Would you be willing to pay $10? Would you be willing to pay $20? Well, if you're following the rule of maximizing expected value, you would actually be willing to pay any amount of money to play this game. Okay? Because as it turns out, the expected value of this game is infinite. It's infinite, the expected value of this game. Okay, let me show you why. Okay. So we're going to fill out some outcomes here. Okay, so the outcomes in this game are basically going to be, well, what are the outcomes of this game? So I could either get, for example, I could get a tail. I could just get a tail on my first flip, in which case the game is over, right? Or I could get a head on my first flip, so I would win the first flip. I would win $2, and then I could get a tail, and the game is over. Okay, in which case I would win $2. Let me fill out my payouts. Okay, so if I just get a tail, I get nothing. If I get a head, I win $2. Or if I get a head and then a tail, I win $2. Say it keeps going twice in a row. So I get heads twice in a row, and then I get a tail. Then I would be paid $4. If I get head, 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 so I get real lucky, 3 heads in a row, and then tails, I get paid $8. Head, 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 tail, I get paid 16. Okay, and so I'm just going to kind of put etc. here, and then I'm just going to extend this pattern all the way down. I'm going to say each cell is going to be equal to twice times the previous cell. Okay, so let me just extend that pattern all the way down. Okay, and then let me do the same thing over here. I'm going to look at the probabilities. Okay, so what's the probability that I would get, for example, I would just lose the first outcome? Well, it's 1 in 2, or 50%, right? What is the probability that I would get a heads, though, and then lose on the next one? Well, the probability of that is also 1 in 2. Okay. Now, what is the probability for me to get 2 heads in a row? Well, the probability of 2 heads in a row is 1/2 times 1/2, or 0.25. In other words, it's half the probability that I would only get 1 heads in a row. Okay, so here my probability is 1/2 times 1/2, or 25%. Okay. What is the probability of getting 3 heads in a row? The probability of that, as it turns out, is 1/2 times 1/2 times 1/2, or 1/2 raised to the power of 3. Okay? So basically, in each situation, you're half as likely to get it as, you're half as likely to get 4 heads in a row as you are to get 3 heads in a row. So basically, this probability, every time we're going to be multiplying this by 1/2. So I'm going to do that. I'm going to do this value times 1/2. Okay, and I'm going to basically extend that calculation. Okay, for all of the different possible outcomes. Okay, so now you can see that when I do this, something interesting happens. Okay, so basically what's going on is my probability of winning in each one of these scenarios is getting cut in half, but my payoff at the same time is getting doubled. So my probability is getting cut in half, my payoff is getting doubled. So when I multiply these two numbers, it's sort of a wash. It ends up breaking even, and I always get 1. All right, this is 2 times a half. This is 4 times a quarter, 8 times 1/8. I just always get 1. Okay, and how many of these potential outcomes are there? Well, it's infinite, right? Like, I don't have enough rows in this table to represent the full set of possible outcomes, because it is theoretically possible, even though it's very unlikely, it's theoretically possible that I could be playing this game for like 20 turns or 30 turns. Okay? And so to calculate the expected value of all of this stuff, right, if I were to, extend this table and calculate this thing all the way down, and then I were to add all of those expected values, what I would essentially be doing is adding up an infinite number of 1s. Well, you add 1 to itself an infinite number of times, you get infinity. Okay, so the expected value of this game, of this St. Petersburg paradox game, is actually infinite. Okay? Now, does that mean that you ought to be willing to pay like an infinite amount of money to play this game? Well, I think most people would agree that they would not be willing to pay any amount of money to play this game. Okay? So once again, if we're going by following the rule of expected value, we sort of have a paradox. Okay. Now, as it turns out, though, this paradox is resolved if we again use the concept of expected utility, not expected value. Okay. And so let me perform the same calculation, except I'm simply going to use the expected utility. And I'm going to assume the same utility as function as last time. I'm going to assume that it's basically equal to the square root of the amount of money I'm going to win. Okay. So if I fill this formula that we had from last time all the way down, the square root formula, okay, you can see, okay, here's the square root of all of these numbers. Okay. And let me get the computer to round these a little bit so they're a little bit easier to read. Just round to 3 decimal places here. And so you can see what's going on is now when I take these utilities, you can see that they're much smaller, and multiply by the corresponding probability, I don't get 1s all the way down. I get initially a pretty big number, but then that number goes down and down and down and down and down. It gets smaller and smaller and smaller. And in fact, it's getting smaller exponentially. So when you take the sum of a number that's getting smaller and smaller exponentially, even if it's an infinite sum, the number that you get is actually finite. So we find that the expected value of this game is actually close to 2.5. It's not an infinite number. It's a finite number. And so if you're using the concept of expected utility, you wouldn't be expected to pay an infinite amount of money to play this game. You would just be expected to, basically pay whatever amount of money corresponds to this expected value, this expected utility of 2.4 units of utility. Okay. So let's just do a quick recap. Okay. In this lecture, we discussed the concept of decision-making under uncertainty. How should a person go about making decisions when there's risk or there's probabilities involved? Okay. And we talked about one potential answer to this situation, which is that faced with an uncertain situation, we ought to act according to the rule of expected utility. This was the rule that Amy Duke was proposing. Okay? And we find that in many situations, I'm sorry. We ought to follow the rule of expected value. That's the situation, or that's the solution that Amy Duke was proposing. In an uncertain situation, we ought to maximize expected value. Okay, and we saw a number of examples of this. For example, we looked at the situation of monopoly. Okay, we looked at the situation with a lottery, and we learned how to calculate this expected value. Okay, and following the rule of expected value, or maximizing expected value, that's a good rule. Okay, it's a very useful rule. But we found that there were a few situations where this rule appeared to not make sense. But we find that if instead of maximizing expected value, we just tweak this rule a little bit, and we add in the fact that it's not money that people want to maximize, but utility, and we take into account the fact that utility has sort of diminishing returns in the amount of money that you actually have, well, then we can make sense of these situations too. And so instead of, we just need to modify Amy's rule slightly. Instead of saying that people maximize expected value, if we assume that they maximize expected utility, okay, we can really come to understand or make sense of a lot of decisions that involve uncertainty. Okay, so complete the questions along with these videos, and then just like before, the homework assignment is actually in the same document. It's just your homework is just the very last part of this document. Okay, and all of that will be due next Tuesday at 4:30 p.m. All right. Enjoy your weekend. Stay safe. Stay healthy. Okay. And I'll see you guys next week.